Good evening and welcome. I'm Jim Plummer, the Dean of the Engineering School, and I'd like to welcome you all to our first EngX event. This is actually an experiment for us in the School of Engineering, and having an event like this, and as you probably have gathered, it's modeled sort of after the TEDx events that have become so very popular. But we really would welcome your feedback at the close tonight and or in the future as to how much you like this kind of a format for these sorts of events. Our goal is to provide an evening for you that will be both interesting and reconnect you with some of the things that are going on in the School of Engineering. So in addition to a big crowd here in the video auditorium, we have actually several hundred alumni and graduates of the school watching in the live webcast that's going out over the internet. So tonight we have three short talks, roughly 15 minutes each, from three of the school's leading authorities in an area that's commonly called big data. Big data, as all of you know, is sort of about the analysis of or extraction of meaning from large data sets, and it's being used today to make decisions in a whole variety of fields, ranging from business to healthcare to social networks, and you're going to hear tonight from three of our faculty who are working in the big data or data science area, and they're working in different application spaces, the first being healthcare, the second being social networks, and the last one being associated with climate change. So I'm going to be very brief here and just introduce our three faculty speakers and then let them each speak in sequence for 15 minutes or so, and then we're going to leave time at the end for questions. And so if you have questions, we'll try and hold them until each of the three have finished speaking. But we will have plenty of time at the end for questions, and there's an hour at least social event afterwards, and we'll all be around if you have other questions that you want to talk with any of us about individually. So our first speaker tonight is Russ Altman, who is a professor of bioengineering, genetics, and medicine, and he's going to describe how he's mining data to discover new medical knowledge. Russ combines large data sets from public health sources, from electronic medical records, and from web searches, and he's gaining new understanding about drug responses by mining information from these large data sets. Jure Leskovec is an assistant professor in computer science who views the web, interestingly, as a sensor that captures the pulse of humanity. Jure will outline what he's learning about human behavior by mining large social and information networks. And our final speaker, Chris Ray, is also an assistant professor of computer science, and he's actually almost a brand new faculty member here at Stanford. But he's collaborating with people in geoscience to build a database of biological remains, information that could help us better understand climate change. So three quite different topics, but all associated with sort of extracting meaning and extracting information from large data sets. So I think without further ado, Russ, if you would kick it off for us.
Great. Testing. Good. Thanks very much, Jim. It's great to be here. Good evening. I should also say that I have a courtesy appointment in computer science just to complete the clean sweep throughout the department, and I value that appointment. So these, I'm not going to use any slides. I apologize. These are two pill bottles, and I'm a physician, I should also mention. So in my free time, I'm an internist, a board-certified internal medicine. I practice a little bit, and then I do a lot of research. But I do prescribe drugs. And the thing about drugs that you may know is that they're perturbations of your physiology with an intended effect that's hopefully more good than bad. The problem is that they are generally approved by the FDA based on a single drug and its ability to be both safe and efficacious. And very rarely, when the FDA approves drug A, does it consider all the drug Bs that you might also be taking. But when we look at the population, especially the aging population, we have the average 70-year-old is on 7 medications and has 3 or 4 or 5 chronic diseases that are being treated. And we tend to make 5 or 6 independent prescribing decisions, trying to optimize for each of them locally, but with no sense of a global optimization of the treatment of the patients. And so we're worried in our work about what all of these drugs working together might do both good, which means it may be that 2 drugs together get better outcomes than either one alone in the setting of multiple diseases, or worrisomely, we might be giving two drugs that actually individually each one is meritorious, but together they cause problems. And so I just want to tell you a story today about, I don't want to hold these both, so I'll just hold the big one. I want to tell you a story today about a series of things that happened in our lab in the context of big data that helped us make one discovery that might have some public health implications. So it all starts with the FDA, the Food and Drug Administration in the US, which, to their great credit, collects reports of adverse drug events that occur nationwide. These reports can be provided by physicians, pharmacists, drug companies, and the FDA takes them and almost immediately puts them on a website where you and me can download them immediately. And they've been doing this for years, so there are millions of such reports. That's our first source of big data, the FDA adverse event reports. And what do they look like? Pretty simple. They don't have any names or identifying information, because that wouldn't be right to put on the web. Although Jure can probably infer who all the people are. He'll tell you about that later. What they have is the list of medications that the patient was on, the list of diseases that they have, and the list of side effects that they experienced. Pretty complicated, because they don't tell you, we think this drug was causing this side effect, or this disease was causing this side effect. You just get those three lists: the drugs, well, the diseases, the drugs, the side effects. But this is a great data set, and I have a biomedical informatics student in the biomedical informatics PhD program who was in my lab. He said, Russ, we got to mine this. We have to look for the ability to pull out new information. I said, yep, that's what the lab does. Let's do that. So he built a classifier. That is to say, he looked at the data for drugs that were known to change glucose. There's a bunch of drugs we use for diabetes that lower glucose. There are other drugs that we use, but they happen to raise glucose. He looked at all those drugs, and he built a classifier. And I'm not going to go into the technical details. There's not enough time. But this is all published, and we can get the papers for everybody. But he built a classifier that looked at patients, based on all this data, he looked at patients who were on these glucose-altering drugs, and he looked at the side effects that they experienced. And he said, can I find a pattern of side effects that's associated with drugs that alter glucose? And he built such a classifier. And he validated it because he knows he had a lot of training examples, so to speak, of known glucose-modifying drugs. And he ran it, and he came into my office and said, Russ, I can predict drugs that change glucose with 94% accuracy. And I said, Nick, that's great, but nobody cares, because every doctor knows the drugs that change glucose, because that's what we learn in medical school. So good job. But, nobody cares. He said, but he's a smart guy. He said, Russ, I thought you would say that. He said, but I also ran the algorithm on people who were on two drugs, neither one of which has a glucose-changing signal alone, but together, they change the glucose. I said, well, that's interesting, because especially if neither one of them alone, then that's almost by definition a synergistic effect. And so he showed me the list of and he had a pretty long list, 20 or so pairs of drugs that had a pretty strong signal together, no signal separately. And on that list, this is where being a doctor was handy, I saw an antidepressant that I've subsequently learned is taken by about 16 million Americans. It's called Paxil or paroxetine, and a cholesterol drug called Pravachol or pravastatin that is also used actually by about 20 million Americans. And I said, well, those two, if that's true, if they're changing glucose, and his prediction was actually that they would increase glucose. I said, if that's true, that's a big deal, but nobody would believe you based on this data mining mumbo-jumbo in the FDA database. So he said, okay, what are we going to do? I said, well, we have the Stanford electronic medical record, and that's been de-identified, so the patient names and addresses and all that has been taken away for the purposes of research. I said, let's go into the Stanford electronic medical records and let's see if patients on those two drugs have evidence of glucose changes. So this is now going to be our second big data source, electronic medical records. I mean, it's really big if you go nationwide, but even at Stanford, this is covering 3 to 6 million patients. Now, we needed patients who were only on these drugs, but we needed a patient who was on one of the drugs and had a glucose measurement, then got the second drug and had another glucose measurement, all within a reasonable period of time. So there were 11 patients in the entire Stanford medical record. So there were a lot of patients taking both drugs, but only 11 who had one drug, a glucose measurement, the second drug, and another glucose measurement. All 11 of them had their glucose going up, and even within a sample of N of 11, it was statistically significant. So he was very excited. Now he was getting my attention, and I said, Nick, this is awesome, but still, you did FDA mumbo jumbo, and then you had 11 patients, and that's just not enough to get the FDA to like give a warning. So what did we do? We needed more electronic medical records. We called friends at Vanderbilt, which has a big electronic medical record and an informatics research effort, and Harvard partners. And we explained what we were interested in, and miraculously, they agreed to run the same queries locally in their data. Vanderbilt had about 30 patients. Harvard had about 100 patients, so we got to about 140 patients. And what we noticed was that, this is for non-diabetic patients, their glucoses were going up on average, and statistically very significantly, 20 milligrams per deciliter. So to give you some context, you're walking around, if you're not diabetic, you're walking around with a glucose of 80 to 90. A glucose of 125 or above is signs that you might have glucose intolerance or type 2 diabetes. So a 20 milligram per deciliter bump is getting you from the normal range right on the border and potentially over the border into diabetes. So that was significant. So this was now getting to be very interesting because we now had 150 patients across 3 electronic medical records across the country, all with a high glucose. So now we said, this now looks convincing, let's write this up. And we wrote it up, but just to make sure, this is little data now, we fed the drugs to mice. So we submitted the paper because we believe in informatics, but we also know that there are reviewers out there who are very strict. And so we fed it to mice while the paper was being reviewed. And it was very nice because they accepted the paper just on the informatics data evidence, but the sugars in the mice went up. And so in a note added in proof, we said, and by the way, when you give these 2 drugs to mice, their glucoses go up. So that was very satisfying, and 2 data sources, and we were very excited, and it got a fair amount of press because it was a nice example of doing a data mining to make a discovery, electronic medical records to do a confirmation. But we were talking one day and we said, you know, I wonder if patients on these 2 drugs are sensing the symptoms of hyperglycemia and doing Google searches. So we wrote a proposal to Google saying, could we please have your search logs? And they couldn't have, there's probably Google people out here, they couldn't have said no any faster. So I was sitting around with a friend of mine who works at Microsoft Research, and I was saying, you know, we have this great finding, and I would love to do, he said, well, we have the search logs of Bing. And so, you know, I said, well, no offense, but it turns out that if you use Internet Explorer, many people who used Internet Explorer have said OK to a pass-through that allows Microsoft to save the searches not only on Bing, but on Yahoo and Google and Alta Vista or whatever. So they actually had quite a lot of, and he assured me and his lawyers assured me this was all legitimately collected. He had search logs with the IP address of the search over time. So we said, OK, let's do the following. First of all, we said people are not going to just search for hyperglycemia, but we defined 50 words that are related to hyperglycemia. Hyperglycemia itself, high glucose. But there's other symptoms that go with hyperglycemia, like lethargy, fatigue. Came up with a list of 50 words. What we did is we looked in the search logs for searches where the person searched for one of the drugs and any of those 50 words, or another one, the other drug, and any of those 50 words, and compared those rates of search with the people who typed in both of the drugs and any of those 50 words. And somewhat to our surprise, there was a 10-fold greater frequency of searching for the 2 drugs together and diabetes or hyperglycemia-related words than either drug alone. So that led to another paper where it was called, you know, the wisdom of the crowd, something about the crowd. The crowd, basically, patients are telling us what the side effects of their drugs are, because what would we all do? You take a new drug, you have a funny side effect, especially if it doesn't go away, you go to Google or Bing, you do a search. And those searches tell us and the number of those searches is great enough that we can infer what's going on. And so the point of this paper is, and by the way, all of these searches were done before we published the paper about the side effect, because we were worried that the press associated with the report of the pravastatin and paroxetine causing hyperglycemia might lead people to get worried and to go do a search for other reasons. But we had search logs from the period before we had ever published it, so this was kind of well controlled. And that was exciting, and it was our third data source, and this was the crowd. Very exciting, because now we've talked to the FDA, who to their credit has an office of social media. And they're interested now in looking at search logs in collaboration with Microsoft, because Microsoft is willing to share. They are also working with a group that is not our group, that is looking at Twitter feeds. Believe it or not, and we might hear a little bit more about this, people tweet their drugs that they're on and the responses that they're having. I do not know if that was a design feature of the Twitter product, but they do it, and I didn't believe it until I saw tens of thousands of tweets that these guys at Harvard had collected saying that, and they can do sentiment analysis where they say, this drug is occurring, and the words we're seeing in the tweet are showing dissatisfaction. Versus, and in other cases, they have words that are showing satisfaction. And so the FDA is now seriously considering, we've had already a meeting in September, about can we, as they roll out new drugs to the public, can we now do surveillance for not only single side effects, but for interactions, such as the one we discovered, based on these social media. So that's all where we are now. It's very exciting. That's the story that I wanted to tell. With respect to the paroxetine and the pravastatin, the antidepressant and the cholesterol medication, we are working with the FDA to see if they can replicate our signals. First, we have to tell them about our methods, because these methods are not the methods they typically use. In fact, the first line of our paper said, standard FDA methods will not find this. They read the paper, they called me up, they said, Dr. Altman, our methods won't find this, we can't replicate your finding. And I said, did you read my paper? The first line was, you won't be able to see this. But it's a problem for them, because they have a serious duty to the nation to use validated methods that have been proven, and they can't just take some wacky Stanford professor's algorithm, which, although I believe in it, it hasn't been validated broadly in the community. So they're in this tight position right now, but they're rapidly trying to reevaluate their stable of algorithms and include these kind of newer data mining and big data mining algorithms so that they can use that in their surveillance. So that's the story that I wanted to tell. The work continues, and it's, I think, an example of where, the final point I want to make is, all of this data in your electronic medical record, in your searches, is it possible to misuse it and use it in ways that are nefarious? Absolutely. And Mr. Snowden hasn't done any of us any favors with the NSA thing, but I want to stress that these data also have unbelievable power to unlock new biological and medical discoveries. And so it would be a terrible thing to lock down this data with a blunt method that doesn't allow us to continue to make these discoveries, because I think we've only begun to scratch the surface. And so as a side project now, I'm trying to figure out how to make sure that these data can be shared in a responsible way, respecting privacy and confidentiality, but not turning off this spout, which I think is incredibly difficult. So with that slightly preachy point, I'll stop, and I think we'll have questions at the end. So thank you very much. And now I'm pleased to introduce my colleague, Jure Leskovec, who's from the computer science department.
OK, great. So can people hear me? Yeah? So what I'll talk about today is how the web is the sensor to the humanity. So let's think about the web, right? What do we have on the web today? We have a large number of online computing applications, right? So everything from blogs, social media, social networks, various kind of communication applications, and so on. And the question is, what do these things have in common? Right? So what these things have in common is that they allow us for rich and dynamic interactions between the people and the content that people both create and consume. So the difference is that traditionally the web was thought of as a static library where we basically go and just browse it. Today, the web is really where we interact with each other. And if this is the place where we interact, what more is there? Another important thing is that this is large scale. So what this means is that it's being used by billions of people all over the world. And the interesting thing is that when we are using the web, what's happening is that basically everything we do on the web leaves a digital trace. right? So basically the usage patterns, interaction patterns, content created patterns are logged, or they leave some digital trace that can be studied, okay? So in a sense, what we can think about the web today is that this is basically our laboratory for understanding humanity. Basically, it allows us to capture and see things that have been going on for millennia, but we never were able to see them. Now we can actually see them at a very fine granularity. So if you think about this, right, what this means is basically that generally, right, the science advances when invisible becomes visible. And this is exactly the case what's happening here, right? Things that were around us from forever were very hard for us to measure and observe. Now we get a very good trace and almost like a telescope, a sensor into all these things. So, right, what is the question? The question is, how can we understand the fundamental patterns of human behavior from these raw digital traces, right? Can we do that? And what I will do in my talk, I'll show you some examples of how we can do that. So in order for us to do that, the first thing we need to kind of take this data and come up with a unified data representation. And it turns out that these digital traces of activity, the way you can think about them is you can think about them through the lens of the networks, right? So the idea is that I can take this data and represent them as graphs, static, dynamic, weighted, unweighted, directed, undirected, where the nodes can be people, can be web documents, can be blog posts, and then there are interactions between these objects or entities. So this can mean communication, can mean friendship, can mean a hyperlink, things like that. Okay, so now that we have a common kind of data representation and we have these large networks, we can start analyzing them. What's interesting is that analyzing large graphs by itself opens a bunch of very interesting technical challenges, both in terms of developing theory for understanding networks, both in terms of the computer science theory and also the graph theory, in terms of algorithms, how do we compute over these massive wiring diagrams or networks, and not even how do we compute in terms of the algorithms and what kind of data mining techniques we need, but also in terms how do we scale up across the machines or even over one single large memory machine, right? Assuming that we are able to do these technical things, which kind of as engineers and computer scientists we do, the question is what kind of interesting things can we learn? So what I'll show you now is kind of two examples where we can learn something about human behavior and not only learn, but also influence it. So the first question I'd like to tell you something about is this process that every one of us has experienced, right? Is how do we become a member of a community? We change a job, we go to a new school, there is some community of people, we'd like to fit into that community. How does that process take place? How do we become members of those communities? So the idea is the following, right? So if I want to understand this process, I want to have a way to measure it. And one way to measure it is to look at the language of the community. So the idea is that language builds the collective identity. So if I can measure how the language of the community and how the language of an individual change over time and how they relate to each other, I can basically get a window into this process of how people become members of the communities. Okay, so we will look at the language that is being used in online communities. So now, what is interesting that there, if we go back to the linguistics literature, there is a number of kind of funny hypotheses about how the language changes. So for example, it has been argued that innovation in language comes from adolescent women. So basically women between ages of 16 to 19 are innovators in language. Why is that? It's not clear, right? It could be kind of that this is biologically critical period. It could be a teenage rebellion, things like that. Similarly, it's been observed or hypothesized that the stability, basically the freezing of your language, of your vocabulary, happens for older adult speakers. And the question is, again, why? Right? Is this biological? Is basically our brain getting more and more frail so we can't learn new words? Or is it something else? Or maybe, emotionally, adults are more stable, so they say, no, I won't take on this jargon, thank you, right? So those are kind of the questions. So now, how would I go and obtain a linguistic record, right? So one way is that I take a microphone and I follow a person for 50 years, right? And basically I just record everything that person says. That would be one kind of, this would be the old way of doing it. A different way of doing it is that I go and I collect a complete linguistic record of some of online communities, right? And what I'll show you now is examples of 2 online communities for which we have their complete linguistic record over more than 10 years. So this means that for every kind of post, for every communication that happened inside this community, we have a record of it. And we choose 2 very different domains. So the first one is the domain of online beer reviews, okay? So let me just read, like this is a kind of, I will read you a review and you will see that this is highly technical community. So it goes like this, okay? So clear copper colored brew, medium cream colored head, floral hop nose, caramel malt. Okay, so that's how an expert talks about beer, right? So precise, clear, unemotional, things like that. So this is kind of the first community we look at. The second community we look at is an online discussion forum for women with breast cancer disease, right? And here again, basically, what is happening is that these women that are learning how to talk about their disease, express what's going on, in both in cancer and in beer, people are coming up with new words, they're learning new words, the language is changing over time. So our idea is to look at this linguistic record and try to see how is the language changing as a function of time. So what I'll do, I'll show you results for beer just because kind of it's more fun, but everything also is true for breast cancer as well, okay? So here is a first example of a beer community. So what I'm showing you on this graph, the x-axis is time and the y-axis is the usage of a particular word. So here I'm showing you usage of 2 different conventions. So a beer has a smell, and as an expert reviewer, you need to be able to express how the beer smells. So you can use what was called the aroma convention, when you say aroma semicolon and then describe the thing, or you can use the smell convention, which means you use a capital S, semicolon, and then describe the smell. So these are 2 different ways to talk about the same thing. And what do you see? You see that in 2003, the usage of aroma peaked, and then later on in 2006, 2007, the smell convention took over. And the question is why? So to answer this, let me kind of unpack this mystery maybe a bit more. So here is a graph of the smell versus aroma convention for users who joined in 2003. And there on the right is the same kind of graph, usage as a function of time, for users that joined in 2005. So what do we see is that users who joined in 2003, they keep using their aroma convention. Basically, they don't react to the smell convention. People that join in 2005, they ignore the aroma convention and start using the smell convention. So how could we unpack what's going on? So there are really 2 things that are going on. So one thing that is going on is that individual users are basically evolving over time. And the other thing that's happening is also the community is changing as a function of time. So what I would like to do now is show you an example of an individual change, how basically an individual person changes over time. And then I'll show you something about how community changes over time. And then we'll also look how do these processes interact with each other. So first, how the individual changes over time. So here is one example how users change. For example, this is time versus usage of first-person singular pronouns. This is the review number, so how many posts has a user had. And what you see is that the usage of first-person singular pronouns is decreasing over time, which you can explain that basically people talk less about themselves and they talk more about the beer. Or if you want a different way, you can say that this is a sign of an increased identification of a person with a community. Okay, so here is what happens at the individual level. What happens at the global level? For example, at the global level, fruit words are getting more and more popular. Okay, so what do you see? That back in 2003, fruit words like pineapple, citrus, grapefruit were not used to describe beer, and now they are used more and more. So kind of what's one thing that you can take away from this talk? If you want to be perceived as an expert beer person, you should use citrus, pineapple. How does the beer taste? It has a citrusy flavors in them, right? So that's one thing you can take from here. So this is what happens at the community level. So now what we can think of is think of the following. So think of my x-axis as time, and my y-axis is some kind of abstract axis of how community language changes over time. And it just kind of is some abstract trajectory through this space. What we also know is that users language changes over time. And again, let it be kind of some arbitrary trajectory through this abstract space. So now the question is, how do the two things relate to each other? Kind of, can I measure the distance between the language of the community and the language of the user? And actually, we can do that. We can basically use some techniques from statistical language modeling to be able to understand basically what's the cross correlation between the language of the community and the language of the user. So now that we have that, here is, for example, what happens. So what I'm showing you here is the x-axis is user's lifetime. Okay, so 0 is when the person enters the community, and 100 is when they leave. So kind of when they die from our point of view, right? And the y-axis is the distance from the language of the community at that given time. What you see is that users start using language that is very different from the community, and then they kind of slowly converge closer to the community. So what does this mean? Is that this is what's happening, right? Your language starts away and then slowly approaches that one of the community. Of course, the reason why I'm showing you why I'm not showing you the second part of the graph is because something interesting happens there. So what happens is that before people leave, the distance between the language of the person and the language of the community increases again, right? So one potential explanation would be that the person kind of distances themselves from the community, that maybe they start talking off topic, maybe they get unhappy and kind of they're not using the language of the community anymore, the gap increases and the person leaves. That's one possible hypothesis. Another one is to say that what actually happens is that the person starts adopting and they just remain flat. So basically their language gets stuck in the past, and it's the language of the community that is getting away from the user. And now what I will show you next is kind of a computational experiment that is able to separate out these two hypotheses. And the way you can do this is to take person's language and ask, is the language you are using today, is this more like the language that people used in the past, or is this more the language that people will use in the future? So for every kind of post that a person writes, I can say, does this look like the future or does it look like the past? So if I do that, I'm showing you this here. So again, x-axis is user's lifetime from 0 to 100, and y-axis is whether their posts look like how the language of the community will be in the future, or do they look like how it will be in the past. And basically you see that young users are using progressive language, while old users are using old language, which basically means that this second hypothesis is true, right? Is that the way people age is by stopping adapting the new language. So basically their language gets stuck in the past, and it's kind of the world or the community that is starting to go away from them, okay? And then when kind of this gap increases enough, the people leave. What is interesting though is that here we took all the people and just kind of stretched their lifetimes to be between 0 and 100. What's interesting is that every person, no matter how long they stay in the community, they go through the same life cycle. So we can talk about basically about an elastic life cycle, in a sense that people who stay very short, who write very few reviews, they quickly converge and quickly go away. While people, for example, that stay long, their distance to the rest of the community is much smaller, and kind of their language remains agile much longer. So why is this interesting is because everyone who leaves the community, they basically leave looking old. So regardless of their physical lifetime, everyone goes through the same kind of life cycle. What we can do now is, for example, we can, based on these things that I showed you, we can, based on the language of the user, we can actually predict when the person is going to leave the community, right? So based on how their language started and how it is evolving as a function of time, for example, just using their first 20 posts, we can quite accurately predict whether somebody is going to be a long-term contributor in the community or whether they're going to leave. So that's kind of the first thing I wanted to show you about. The second thing I wanted to show you about is not just how do you measure human behavior and try to understand it, but how can you go and influence it. So the idea here is to ask, how can we create, let's say, incentives in online and also offline communities to get people behave the way we would like them to behave, or to behave well, if you like. So the first question is, what's the incentive mechanism? And one incentive mechanism we looked at is called badges, right? And kind of people work amazingly hard to earn badges. We were actually not the first to realize this. So the first to realize this, I think, was this gentleman who said, give me enough medals and I'll win you any war, okay? So Napoleon figured this out already, right? So And if you think about this, right, there are many examples of badges around us kind of every day. So, for example, science is pretty much run on badges, right? Kind of whenever I get a grant, if somebody gets a grant, they get a publication out, that's in some sense a badge. Nobel Prizes are nice, kind of hefty badges, right? Army, of course, has badges. Online social networking sites have badges. Also, like education sites and Wikipedia actually have badges where they try to stimulate people to kind of do more work. So the question is, why are badges interesting? And badges are interesting because they play multiple roles. They can recognize a wide range of different behaviors or different activities, and they can serve both as credentials, but also as incentives for people to try to obtain them. So what is the question? The question is, how do these badges translate into the effects on human behavior? And again, kind of to see these effects, we need quite a lot of data. So what we looked at is a question answering community called Stack Overflow. So this is basically kind of programmer's best friend. Whenever you don't know what to do, you go to Stack Overflow, you type a question, in 5 minutes you receive an answer, and usually a really good one. So the way this works is there's 2 million people, 5 million questions, more than 10 million votes on questions and answers, and the site has badges. So kind of the more questions you answer, the more upvotes you get, the more badges you get. And today people on their resumes would, for example, say, oh, I got 17 gold badges on Stack Overflow and my reputation score is this much. So it's kind of a serious thing. Okay, so now we have a complete trace of how people are asking questions and how they receive feedback and also what badges they receive. So the question is, how should we think about badges and how are they modifying our behavior? So what I'll do next, I'll show you kind of a simple utility-based model of how behavior changes under the presence of badges. The way we will think about this is that we'll think about our, let's say, Stack Overflow example as that there are two things you can do on Stack Overflow. You can either go ask a question or you can answer it. Okay, so whenever you do an action on the site, you start as a new user at 0, and then you move either to the right or up. Okay, and then how do we represent badges in this action space? They are simply horizontal or vertical lines, right? So what this is saying, as soon as you do 10 actions of type A1, I will give you this badge. Okay, now that I have a way to represent badges, now I need to represent human behavior. The way I can think about human behavior is that it's simply kind of a vector in which people walk, right? So for example, for this person, we will call that they have this preferred behavior where they really like doing action of type A2, but they don't like doing A1 too much, right? They are kind of moving this A2 direction more. Now, the question is, of course, this person, if they keep doing this thing, it will take them very long before they cross my badge line. So what the person will want to do is they will want to maybe change their behavior to get to the badge sooner. So what we will do is to say that the person is going to change their behavior in order to get to the badge fast, but of course changing behavior hurts. It's like exercising. You don't want to do it too much, right? So this is the same thing will happen here. So what we are assuming is that everyone is born with their preferred behavior, and now the badge, you like it, so you will change your behavior kind of as little as possible while still trying to get to the badge. So this is basically the model. So what are the predictions this model makes? So here's the first prediction it makes. For example, this is time, and here is the probability of taking action A1, A2, or A3. Here at 25, we have a badge that we give if a person makes 25 actions of type A1. So what do you see? We see that very far away, the users don't react to the badge. They are this kind of baseline behavior. As they get close to the badge, they ramp up their action of type 1 and at the expense of actions A3 and A2. Okay, but A1 goes up, then they get the badge, and then they just return to the initial behavior. So that's the prediction, right? So users will steer in the direction of the badge, they will get it, and then basically they just go doing their old thing. So that's the first thing. And the second thing that kind of emerges from this is that you can think of these badges as some kind of magnets, right? So here is a two-dimensional example with two badges. And you can think of these vectors as the direction in which the users are moving, right? So as they get close to the badge, they get more and more attracted to it, they get it, and then they go the other way, and so on. So these are kind of things that the model predicts. So now the question is this happening in real life? So here's an example of a Stack Overflow badge that's called an electorate badge. You get it if you voted on at least 600 questions. So there is a question, and you can say this is a good question or this is a bad question, and you've done this 600 times. So the time 0 is the time when you earn a badge, and this is the number of actions per day of a different type. On Stack Overflow, you can do exactly 4 actions. You can ask a question, you can answer a question, you can vote on a question, or you can vote on an answer. What you see here is that just before the people get the badge, the number of question votes increases from around 4 a day to almost like 12 a day. And then after they get a badge, everything drops down to the previous activity, right? And you see that kind of here, in this case, other activities are actually not hurt too much. The yellow activity is hurt a bit, but blue and red, they remain flat. Which means that what happens is that people both steer in the direction of the badge, but also they get more engaged, right? Their total activity on the site increases. So with this, what is now the interesting question we are working on now is not only how do badges change behavior, but how should we place badges to get the behavior change we want? Right, so we can kind of ask an algorithmic question, which is, where should I put, pieces of sugar so that my little ants make the right walk? And given the model, we can kind of, at least in principle, do that. What's interesting is, for example, some of the principles that comes from the model. If the badges are too easy to get, nobody reacts to them. If they are too hard to get, again, nobody reacts to them. But if you just get them right, you will get a big behavior change. So that's kind of the second example that I wanted to share with you. So I'll just conclude kind of what's the bigger theme here. The theme here is that really we have all this social and information network data that is large scale that we can analyze computationally and gain insights about both how to model human behaviors, but not only model it, but also try to influence it. So with this, I'm done, and I'll give you Chris.
Hey, I'm Chris. It's a great pleasure to be here. What I want to do over the next about 20 minutes or 15 minutes is share with you some of my excitement about this new generation of data processing systems we've been building in my group that we call trained systems. And I hope to tell you why we're excited about what they can do, that is, if they can accelerate science, which I'm going to talk about during my talk, and also try and give you a sense of why they're so challenging to build and they keep us up at night and the weekends slaving away on these systems. But before getting to the challenges, I want to talk a little bit about how science is done. So to do that, I brought one of my buddies here, Isaac Newton, one of the great scientists of our time. Someone who invented, calculus in order to solve physics. I mean, it's really just a spectacular person. So Isaac, after he, did all of his great discoveries, he wanted to disseminate them to the world. And like most scientists, he wrote a book. Okay? So he wrote this very famous book, Principia Mathematica. He set out his ideas, and then he distributed it all over the place. People made copies of it, and then they were enlightened and started to work on aspects of physics. Now, it turns out we've been doing that for a while. Isaac wasn't the first, and he's not the last. This is really how science is disseminated today. All of us on this panel write things about, when we have our new discovery, our new result, as Russ mentioned, it goes in a conference paper or a journal paper, or we eventually write a monograph about it and post it somewhere. And so not surprisingly, people over time have collected these monographs, and that's why we have things that look like this. This is the Stanford Library. So over the last millennia, every town, village, city, university has been collecting all of this information, all of these writings from different scientists to try and understand what's going on in the, in the universe really broadly. So relatively recently, something happened about 10 years ago. All this information started going online in massive droves. And one of the more recent efforts, one of the more popular efforts, is Google Books. Okay? So now, with the advent of Google Books, you can enter in a couple of keywords, and back comes, Isaac Newton's great book, even translated into English for you. Okay? And this is a really amazing thing for science. I don't think there's a scientist today who can get by without online resources. I mean, we're using them constantly, and every single day, every single hour even. And you can get this on your phone, your tablet, your laptop. It's really just amazing. So now, the world's scientific knowledge is really accessible in a way it's never been before, and this is a great thing for science. But maybe I'm a complainer, that's why I became a researcher. It's still not as perfect as it should be. Okay? And one of the problems with this is that we're still human. Okay? So the Kindle has made sure we don't have to carry physically all of our books around. But still, you have to, as a human or a scientist, if you want to know about something, you have to read all of those texts that have been produced for you over the last 100 years to have a sensible knowledge of what's going on. And we're simply limited by the bandwidth of our eye and the bandwidth of our brains to be able to suck in all of that information. So we're left in this strange situation. All the world's knowledge is accessible to us. We can enter in a few keywords and get it on our phones. But somehow it's just not readable. It's not really summarizable in the way that we need to be able to draw conclusions about the world's big problems. Like, for example, the problems that Russ was talking about earlier. So some people have drawn an analogy here with the universe, right? So the universe is made up of visible matter, about 4% of it. Then there's this huge mass of energy and matter that's out there that we call dark matter, which is the 96%. And this is sort of an analogous to what we're doing with data today. And people call this dark data. It's this great mass of data that we know is out there, but for whatever reason, we can't access it, we can't digest it, and as a result, we can't make use of it. So this is a situation that we find ourselves in today. Now, making this problem even more pressing, today's pressing problems often require macroscopic knowledge. They require the ability to assemble all those data points that are out there, as Russ mentioned, search logs and different parts of the literature, and bring them together for when the next generation of really interesting insights come about. So we need this macroscopic knowledge. We need something to read for us. Okay? So we work on problems in a bunch of different areas. For example, things in climate and biodiversity. You would love, if you were a paleobiologist, and I know some paleobiologists, you would love to have the entire fossil record laid out for you so you could understand every die-off, every interaction between species throughout time. A lot of that is published, and we don't have access to it. Problems in health, Russ covered this in great detail. Electronic medical records to all of the drug interactions and diseases that people have published all over the place. And finally, things in financial markets. Russ mentioned before that people are using signals like social media and other kinds of text that are out there to predict drug interactions, and foodborne epidemics is another one that's come across my desk. And also things like the financial markets. We know perilously little about how all of these macroscopic systems are really operating today. So I'm going to focus on one in particular that I've been working on with some colleagues. In particular, one guy named Shannon Peters, who's a geoscientist and will be joining us out in Stanford very soon. So as a computer scientist, I look at this problem and I say it's a real failing of our field. We've put everything online. We've made it very easy to search. But why don't we have a machine that can read for us? Why can't it do the job? And so what I want to talk about in the next couple of minutes is why that's a very hard challenge, and one that we've been working on, and a lot of other people have been working on over the last couple of years, and have made some interesting progress, and you're already seeing it today. Okay? So let me show you why this is such a hard problem. Okay? So here's a journal article that we would like to read. I don't expect you to read any of the type on it. I'm just going to use it schematically. Okay? So what we would like to do with a journal article like this, it's from one of these paleobiological journals, is we'd like to go into a table that looks like this, and we'd like to extract information from it and assemble it into a large database. So apparently we have a little formatting issue, but basically what I want to do from here is have this location Obora that I found a particular genus, what happens to be a kind of cockroach that's interesting to someone for reasons that escape me. Okay? So they want to extract, they want to go into this table and pull out all of those different references, all the fossils that they were found and where they were found, at what time period they're from, and put that into a large database to begin to ask these questions. Now this is a challenging problem for a machine because it's got to be able to read through this table and do all kinds of visual reasoning. It's got to be able to know that Obora and this particular genus are associated and do all of that extraction. And the system I'm going to talk about later is able to do that. Okay? But I want to put that aside and point out even a different challenge, which isn't in the reading part of it, the physical part, but is actually in the semantic part. Now it turns out that in the data set that we've collected over the last little while, there are 44 different Oboras, okay? Different places that are referred to as Obora. And we'd like to build a very high-resolution database that's going to tell us which of those Oboras are we even talking about. Okay? So we'd like to link this extraction with it. Now it turns out that if we were able to read the text of this article, it's right there for us. It's got the GPS coordinates, actually, of the Obora we want. And so if we could read that text, we could put that back together. And what I want to get across to you is that the act of putting this table together isn't just having a machine pass over the glyphs. It's actually reasoning about how to combine this information in a way that makes sense and actually resolve things like Obora to the right entity, the right Obora that it's talking about, in addition to doing all that visual reasoning. And these are the type of systems that we're starting to build today and that are so exciting because they can automate a lot of the grunt work that goes on in building these scientific collections, we hope. Okay, so what we want and what I'm going to talk about in the last part of this talk is a machine that can read and reason for us to try and build these macroscopic knowledge bases, we call them. All right. So these systems go by the name trained systems. It's a relatively recent term. We're still trying to figure out how to call them. They actually come out from a bunch of companies. You've probably interacted with one. Maybe some of you have noticed that when you enter inquiries to Google, you start to get what we call structured results on the side from things like Wikipedia. Maybe some of you have seen the system Watson, which I'm going to talk about next. These are examples of systems, trained systems, that involve data, large amounts of data, and some amount of statistical reasoning in them. Okay? So let's talk about Watson for a second so you understand what I'm talking about. So if you don't know Watson, Watson was this machine that was built by IBM. It's now commercialized as a product called DeepQA. And Watson won Jeopardy. Okay? So if you don't know Jeopardy, it's a quiz show, American quiz show. The questions that they ask, for lack of a better word, are sort of these very intricately worded questions that have sarcasm and puns and rhyming and all kinds of stuff. Sort of a uniquely human quiz show. But lo and behold, this little machine here, over the course of 3 days, stomped this guy Ken Jennings, who had won something like 100 times in a row, and was able to basically destroy him. There's a great article about this. If you want, I can point you to it, that described how worried they were about beating Ken Jennings. The guy was a freak of nature. Okay? Anyway, but Watson won. Okay? So that's great. A machine won at this show. You can debate whether or not this is really artificial intelligence. I don't care. It doesn't bother me. It's useful and interesting, so let's talk about it. The thing that was most interesting to me is the way Watson chose to show people what it was doing. So if you watched it, Watson would show several answers that would come back, and each one of them would have a confidence score, a probability associated with them. And I think that's actually something that inside computer science we've known for a while. It's been a revolution in our field over the last 15 or so years that we've realized that the way to be precise, that a computer needs to be precise, and to reason about all the uncertainty that's out there is with probability or statistics. In fact, my dissertation was about probabilistic databases, right? So we've been doing this for a while, trying to understand what does it mean to build these things. Now, these trained systems, these new generation of systems, almost exclusively have this as their way of reasoning. They use statistical reasoning plus lots of data to be able to answer these rich questions. Now, I want to impress upon you that this is a staggering, staggering challenge. So in the system I'm going to show you in a minute or two, we're going to see that we're going to have a random variable, a choice that we're going to have to make about a huge array of things. And the number of choices that we're going to have, the number of decisions we're going to have to make is in the billions. Some of our demos have tens of billions of these little individual choices that have to be made. Each one could be yes or no. But that means that we have to search through this truly staggering number of possibilities, 2 to the 1 billion. That's a number I can't even conceive of how large it is. To put it in perspective, the number of atoms in the visible universe is on the order of 2 to the 300. Okay? That's why this is such an interesting challenge, because we have to search through this efficiently in the time actually it takes you to write a query or for Watson to fire back an answer. Okay? Now we cheat a little, but but that's basically what we're dealing with. That's why it's such a fundamentally hard problem. Okay. So I'm going to show you one application of our system Deep Dive, which is the trained system that we've been building for the last couple of years. And Deep Dive is a layer that isn't tied to any particular application, but one application where we had great collaborators and partners was in this paleobiological and climate change. So I'm going to show you some applications over that. Okay. So the goal is very simple. We want to extract everything that we can possibly extract, paleobiologically relevant facts from the fossil record. And what we're given are a bunch of PDFs. Okay. We're going to go and crawl these PDFs. And then we're going to try and make this cartoonish database of dinosaurs, where the dinosaurs lived. My students make fun of me that I like the dinosaur, but I like the dinosaur, so it stays. Anyway, so we read the text, and we create the database. Okay? And now, as I showed you when we were doing that reasoning about that picture, every little pixel that's there, we try and figure out what word is it representing. Should these characters go together to form a word? What part of speech is it? Are these two words actually related? Are they in the same dictionary? Are they not in the same dictionary? And in this way, when we read millions of articles, we'll get up very easily to tens of billions of articles. Now, this database is a little bit smaller. We only have around 1 billion of those choices to make. But if we can make them all in a sensible way, we can do this extraction task. All right. So we have actually built with our collaborators several databases that they simply couldn't have built without sort of machine assistance. But we wanted to understand how valuable is this? Could we replace what humans are doing? And it turns out that one of our collaborators was building this database over the last 13 years called a paleo database. Okay? 330 volunteers over the last 13 years, 46,000 documents that they've managed to annotate. Okay? Now this database has been truly transformative for their field. They've published 188 papers that they say couldn't have been published without this. Thousands of papers actually cite this database. But 188 that they say couldn't have been done was this macroscopic kind of reasoning that they couldn't do without this database. 17 of those went to high-class places like Nature and Science. And if you don't know, if you're not an academic nerd, those are like the top of the top. That's like, you really made it when you have a Nature or Science paper. That's like, something you brag about to your friends. Okay? So they built this database. So we decided, hey, let's try and turn our machine reading system on and see what we can do. And basically, instead of 330 volunteers, we had about 2 graduate students. Okay? So we said, what could possibly go wrong? So what happened was we were able to very quickly to read about 10 times more documents. And the reason we're limited by a factor of 10 has to do with publishers, and I'll spare you my rant about publications and open access and all that stuff. So we were able to get about 10 times more documents than had actually been read through the system. Now, what it turned out, which in retrospect was totally obvious, was that humans are extremely lazy in annotating these documents. So even though we're reading 10 times more documents, we got 100-fold more extractions, because no person is going to sit through all of those tables and say, this fossil was found there, this fossil was found there, this fossil was found there. And as a result, the machine got a much, much larger corpus of data. Okay? So this wasn't really, in hindsight, too surprising. But the thing that was surprising, and what brings me to why I have hope in these systems, was a very simple and very preliminary experiment that we ran with some of our collaborators. And we pray and hope that this number comes out. Okay? So what we wanted to validate here was how accurate is the system. So if it makes a prediction, how accurate, 80% of them, 60% of them, how often is it? So what we did first is we looked at the volunteers who were making predictions into the Paleo database and compared them to experts. And it turned out that the volunteers were correct about 80% of the time. Okay? Now this is a hard task. I would not get 80% on this, but that's about how often they were accurate. So we looked at this and we said, okay, well 80%. Even if we get 60, 50, at least we're getting so much more data. You can use some statistical magic to be able to make predictions, and maybe it's hopeful and still useful. What was absolutely stunning, and as a result we had just recently, is that on this particular data set, we were in the 90s. Okay? So we were actually able to read this data set and do some of these extractions with extremely high quality. And so for that reason, I don't know that this is going to hold out. We're still in the process of really rigorously validating all of this. But that's why I wanted to share my excitement with you, both about how these systems are built, but also our hope that these trained systems can be used to accelerate at least one little portion of science. Thank you for your time.
So you guys want to come up here? So I think what we're going to do now, we're going to ask all 3 speakers to sit in little chairs up here, and we're happy to have the discussion go in any direction that any of you would like. So who has the first question or comment? Yeah, sorry.
Quick question. So a lot of us here are in technology, and I'd be interested to hear from some or all of you how you're using technology, or how technology is limiting some of the things you're talking about here in terms of 10 to the 1 or 2 to the 1 billion data points, and some of these other, maybe the drug interactions. You've tested 2 drugs together, but there's 7 on average, and how many different hypoglycemia, different sicknesses could you be testing for? How are you limited by technology, or how would technology help you?
So, if I can just from the medication, from my view, the exciting thing about the big data now is, in the old days we took samples, but more and more frequently we're now looking at everything is being measured. So when we have a completely instrumented electronic medical record for everybody in the United States, there won't be sampling. We will have everybody. And so that's both exciting, but it's also scary, because if you don't have enough statistics when you have everybody, then you're in trouble. Because and so we're going to have to have methods. So your question about the technology. The technology is first going to help us measure everything, and I'm quite sure that in my lifetime we will be, in the health realm at least, measuring virtually everything. So there won't be a question of, let's do a trial with 10,000 people. We'll have everybody who's on the drug or everybody who's taking it. So that's the first technology challenge. But then after that, there's going to be statistical challenges of, what do you do when you have the complete sample? There are no more samples to go get, and you still don't have statistical power to make the kind of inferences you want. And my favorite part of Chris's talk was, he said, and we do some statistical tricks and we cheat a little. And I know exactly what he means, because when you have 2 to the million, you have to do something. Very often you have to have a theory in a Bayesian sense. You have to go in with a prior probability and then use the data to adjust the prior probability, because you can't be purely subjective statistician. You have to, or objective statistician. You have to have a a prior, and then use the data to adjust your priors. So I think one of the big challenges, and there are people in the CS department and other places, is creating large-scale statistical, perhaps Bayesian reasoning systems that can take these huge data sets in the combination with very well-informed priors to come up with these inferences that we all want. So that would be my first. The other thing I would say is a lot of this data is moving to the cloud, which is a good thing because nobody wants to run the clusters in our labs. It takes up space where a student could be sitting. And so I'm very happy to have a robust infrastructure where everything gets pushed up there. And also then when I get results, I can turn on that data to be available to my colleagues to check that I didn't make any mistakes. And so there's this exciting momentum towards a shareable, reusable information infrastructure, which I think will advance science. So I'll be quiet there.
Well, I would say my only follow-up to that is, if you think about the hours in the day following on Russ's comment that we're actually monitored, it's actually fairly small. I mean, we have cell phones. They don't have the resolution we want. If you look at the data sets that we're churning through right now, it's text. We're starting to creep into images. We had some meetings about it today. I mean, there's a huge realm of data that's out there that we simply haven't even been able to store and reason about and realize. And so I think that's going to be one of the places where we're sort of tech limited. Jure will tell you and I'll tell you that for a lot of the inference problems that used to be hard for our fields, machines have advanced so rapidly that they all fit in main memory now. We're able to do really sophisticated things with the computing infrastructure that's out there. But clearly, to take that next couple of orders of magnitude, we're going to need innovations all the way from storage to networking to the way things are monitored, all the way to the stuff that is near and dear to my heart, which is working on these large-scale statistical inference. Thanks for the plug. But yeah.
So what I would say, I think really where the limit will be, one is kind of technology will figure out, right? I'm kind of not worried about that. What I think will be important is how do we educate people, right? So now that computation and data science and data mining is kind of percolating to all kinds of sciences, how do we educate these people who did not go through their data structures class, who don't know the big O notation, things like that, right? How do we teach them? And then how do we provide them with tools that are maybe easy to use, that do all the hard magic at the back end, but are very easy to use in a sense at the front end, right? So I think that's where kind of things will have to go, is really how do we figure out computation and make non-programmers program in a sense.
Question?
I have a specific question on the effect of multiple drugs. Is there any data on fatigue? Any data on fatigue due to multiple drugs? Fatigue, effect of fatigue. Fatigue side effect.
The FDA database is a histogram of every side effect and how often it is associated with a drug. The average drug label, so that little piece of white paper in your drugs, has about 60 side effects. And these are the side effects that were observed during the final clinical trial before it was approved. Fatigue is in your top 10. So unfortunately, almost every drug causes fatigue. And so, the worry is that combinations of drugs will cause huge amounts of fatigue. Unfortunately, diseases, being sick, also makes you fatigued. So this is where the statistical inference and trying to tease out why you're fatigued because of your disease and why you're fatigued because of your drug is a thorny problem.
So for Russ, professor in the middle. So going back to your story, I have a two-part question. So the first part is, why the initial focus on rising glucose levels? Did you tell the graduate students specifically to look for those, so interactions with those drugs? Okay. And two, was there a larger purpose towards that? Like, were you trying to say, develop a predictive model or a predictive analytics regarding multiple drugs and causing side effects?
So the answer to those two questions is actually the same answer. So the question is, why did we even do this? Like, I presented, we had the FDA database, and it was just there, and we did something. So we were actually, but the lab is still very interested in discovering combinations of drugs that can do good things. So the question is, are there drugs on the market today that if I use them together will be useful for new purposes, separate from what they were originally developed for? This is very attractive because these drugs have already been shown to be safe. And so And if I can find new uses for them, this could be a new and quick addition to the formulary. So we were actually looking for pairs of drugs that would lower glucose. That would be a new diabetes medication. And so the part of the story I didn't tell is Nick came in and said, Russ, I can't find any pairs of drugs that lower. I just found these two I never heard of that raise. And I said, whoa, but that's 1 million Americans on them. So it was purely a failed attempt to find, and I haven't given up on this, but that particular attempt was a failed attempt to find 2 drugs that together would help treat diabetes. In fact, we found 2 that together might cause it.
But there was a large.
And the higher level thing is, can we figure out how to use drugs so that we get globally optimal combinations of drugs as opposed to a bunch of locally optimal drugs that together are far from globally optimal?
Question over here.
So I think we're all, this is the School of Engineering event, we're all technically, scientifically minded people, and we all get very excited by this, but we're also subjects in these experiments as well. And so as a subject, I worry a little bit, like, well, how, what is the effect of your research going to be on public health policy? Am I going to be denied insurance? And maybe because I'm old, I'm about to leave the community by your trend, but I feel creeped out by Google ads that because I've searched on one page once, suddenly every other website I go to shows me an ad for that page. So just knowing that we are providing all of this information, where's the moderating effect of public policy or bioethics, or what do you see as the more societal or cultural changes that are going to have to happen? Are we just going to have to like adapt or die, or should there be a moderating effect?
So who wants to take that?
I have a so first is a funny answer. Given my talk, right, you are getting stuck in the past, right? But sorry, right? No, I think the questions you're raising are very important, and I would say we are very at least in terms of research, we are very cautious about them. Both in terms that all these ethics reviews that we have to go through, also everything kind of. We kind of never, if I talk about privacy and then I'll jump up, right? So in terms of privacy, we kind of never look at the data by hand because it's too much of it. So it's always kind of looked through by an algorithm. And we never kind of care what's the name of the person, where they come from, we are just interested in these kind of global statistical models of what is going on. So in this respect, it doesn't, we never look at the data by hand. I never go and look at the raw data. The algorithm does that for me. But I think what is important, on the other hand, is that kind of the web is getting scary from time to time, right? You search on one site and then you search for a sofa somewhere, and then the sofa pictures are hunting you for 3 days, and then you say, oh, I'll buy new skiing boots, and then it's skiing boots all the way, right? So that's a bit scary. I think what is happening and what will happen is that in some sense it's this kind of a duel of, everyone is users are pushing a bit, companies are pushing back. And I think as a society, we'll learn where that boundary is. But kind of things are moving so fast that we haven't even figured out where that boundary is. And discussing and thinking about this, I think, is very important.
I totally agree with that. I mean, there's a great example for health privacy. So Americans are very concerned about their health privacy. But guess what? This has been documented, French people are not. Why would French people not? It's because a French person has guaranteed health care for the rest of their life till their death. So they say, go ahead and find out about my diseases. I don't care because I'm not going to lose insurance. I know that I'm covered, and I'm not going to be discriminated against. It's a different story in the United States because of the way our system works right now. You could be declared uninsurable, although Obamacare is trying to address all of this, but at least 2 years ago, and still in many ways. So, but the point is, I think that Jure is making, and that I agree with, is that there are interactions between our expectations about privacy and our behaviors. That's why I pointed to you initially, and the incentive structure that society sets up. And just as he said, we have not yet responded to the availability of this data and the availability of these opportunities with new societal regulations. And therefore, we find ourselves in this really weird situation where we can do a lot of things that are potentially valuable, but are also very worrisome under current rules of engagement. And I am a little nervous about whether our society is able to respond fast enough. And so I think for now it's up to people who are doing the work to exercise appropriate self-constraint so that we don't do something that gets on the cover of the New York Times and they close down the whole operation. So right now it's a self-government which is working okay, but you get worried about that as a long-term solution because there are bad guys who might try to do bad stuff.
Yeah, I think my question is related to this topic. How are you encouraging both public and private organizations and institutions to share their data? I mean, there's new ways to obfuscate the data to ensure privacy per HIPAA regulations. Is there something that seems to be working to encourage pharmaceuticals or healthcare organizations, providers and payers to open up and share this data and yet ensure privacy?
So I can give 3 examples real quick. NIH has a great hammer, which is they write the checks. So most NIH data that is not human identifiable, like not my medical record, but lots of other data gets put on the web very quickly, and there's a great ethic of data sharing because they say you're not going to get your next check unless you share the data. It's a little trickier though for a patient medical records for clinical trials because there's a worry about privacy. With respect to hospitals, they are increasingly seeing that de-identified data sets, especially when shared across healthcare systems, can give CEOs pre-competitive information about their patient mix, about where their claims are all being paid to, that is of great value to them. And so there's starting to be cooperatives that are sharing data. And so that's working okay. Pharmaceutical industry and drug companies, very difficult. I wish I had a dime for every conversation that sounded good and then led to no data. They are just in a situation now because of their relationship to the FDA and the relationship to the stockholders that they're very worried that they're going to release data and somebody's either going to find out that they did something wrong that damaged patients and they're going to lose money that way, or somebody's going to make an incredible discovery where the stockholders are going to say, why the heck didn't you do this data mining and discover this? So it's much better for them just to not share. And so that may change, but that's going to be a tough nut to crack. I would love to get my hands on some of that drug data for obvious reasons. We think we could mine it, but right now it's been unavailable.
So what's happening more broadly in industry is that basically, I think what's kind of going on is the following. There's this hype that helps us a lot called big data or data science or predictive analytics, right? So, and companies, organizations realize that they have value in their data, but they have no clue how, or they have no expertise how to get it out. So that in some sense helps us in terms of establishing like relationships with foundations, companies, other types of organizations to share the data. So putting the data just on the web can be very tricky, right? But establishing a kind of a trust, an agreement with someone to work on their data, that is possible. So for example, in my group right now, we work on criminal court cases trying to help judges make better decisions when they decide who to keep in jail and who to put on bail, for example. So we have 3 million of those court cases working with a particular foundation who wanted kind of our expertise. We work with Twitter, Facebook, LinkedIn, where kind of we work on their systems and on their data, so kind of it's on their servers where we do analysis. So there are very different, there is no one recipe, there are many different recipes how to establish these collaborations, but it's possible and it's been extremely kind of fruitful for us because it allows us to do science and kind of be able to tell stories like I told you, and also it helps them because they learn something about their data that they didn't know before. So we definitely do a lot of this.
So I'll take just a couple more questions right here.
So to your social network graphing thing, I think what you said is that the length of time, you did all of your experiments on length of time in a community, not on the age of the participant. So it's uncorrelated to age. So youngsters getting on Facebook or Twitter or Snapchat have the same model effectively as older people. So there's no correlation between the length of time someone gets to a particular community or the shape of the curve.
Great. So you summarize it nicely. So it seems that there is no connection between biological age and your ability to fit or remain flexible in terms of your language. So it seems it's something else than that, you know, depending on how, very initially early on, you see how nicely and how quickly is a person starting to fit kind of linguistically in the community, how quickly are they getting rigid, that will tell you when they are going to leave.
And have you discovered, or have you looked at the things about the community that will change the shape of that curve, that engagement curve, from longer, slower to shorter?
Not yet. So what we are looking right now is, first thing we are looking at is what are the mechanisms for people to adopt conventions, right? Why do certain kind of linguistic conventions they are adopted, and why are some not? And then the other thing we think that is important is that this idea that there is this initial stage where you learn the language and then your language freezes, what this in some sense allows us to do is to be able to speak to our mothers, right? In a sense that I learn the language from my mother and then kind of I freeze, which means that if my mother would be learning the language and I'd be learning the language, then after kind of 10 years, I'll have my own vocabulary, she'd have her own vocabulary, and we couldn't talk. So we are now looking kind of more at the high level, what does this say about the evolution of language and how the language is being transferred from a generation to generation. So these are some implications of this kind of beer research.
Corner?
Also in regards to the second talk about social networks and how people adapt to entering a certain community, I was wondering if you've looked at the correlation between how long somebody was in a previous similar community, for example, if their behavior adapted towards the community curve at the beginning, and then it kind of sounds like your research shows that it would stay constant because they get used to speaking in a certain way. But have you looked at what happens if somebody who entered and then got used to a certain type of behavior entered a different community, and like how their previous experience would change how they would adapt in a new community?
That's an excellent question. So the question is what happens when people switch communities and so on. So this is actually also something we are looking at right now through some other data where we have comments on newspapers. And we basically see on CNN and on Fox News and so on, how basically where people leave comments and how do they migrate. The thing is, right, for this kind of study, you need even more detailed data, right? So here we have 10 years of complete linguistic record. Now you would want to be able to have this for multiple communities and be able to trace people across. So that's kind of, you're asking for a lot in a sense in terms of the data. So this was, right? So we are trying to look at this, but it's very hard, like, because now you're saying I want to trace, like, right? It's kind of scary.
I'll give you the name of my Microsoft friend.
One more question.
It's a very exciting talks, but I would like to ask about, you all develop software for all of this analysis. Are you going to offer APIs to this software? So for the jargon, like if I want to go, for example, just go and explore, do a search engine if drug A, drug B, and drug C will cause this. Would this be able to automate it, or do you need, because you have only so many graduate students, I guess.
I definitely have only so many graduate students, and we haven't made we do tend to release the end result of the calculation because this is Excel spreadsheet and it's easier. We don't tend to make APIs because we don't have servers. Although with the cloud, then it becomes possible to say, let's just leave a little daemon running who can then do these calculations. But up until now, when we've been doing it on our own servers, we just can't afford to give away this computational cycles. But this is kind of what I was getting at the end when I said the future holds a world with virtual machines and with the cloud where you can have a snapshot of the entire environment that you use to do your research. And then colleagues can go in and test your hypotheses. It's a level of transparency that's a little bit scary for academics because we're very competitive as well. And as you know, it's an act of courage to say to your competitors, here's everything I have, knock yourself out. But I think there is in areas where we're moving towards this, and that should be pretty exciting. For example, I'm going to call Chris tomorrow because I have another domain, not paleo databases, where I think his stuff could be extremely powerful.
And I would add on it, just there is a sort of a movement within a lot of the computer science faculty to put almost everything online. So all of the software that we talked about, I know Jure has a bunch of software packages online. Our stuff is online. They're used by tens of thousands of people. They tend to be people who are, very savvy about a particular analysis and things like that. But we definitely think it's another vehicle to have impact, which is relatively recent as well. So it's a great question.
I mean, so all our code is on GitHub. We make all kind of as many of our data sets as possible available. That has had kind of like amazingly surprising, I don't know, impact in a sense that if there is a graph analysis paper, the way you recognize it that is using our data is by file names because they use the file names I kind of invented or something. So it's interesting how this data is percolating, how the code is percolating. We were surprised that people are afraid or scared of C++. So we are now building kind of a Python front end for our C++ backend. So we are actually kind of to give things back to the community, whoever that is, under the BSD license. So you know, compile and suck it in.
And it's kind of, I just want to point out, it's kind of terrifying. I think you've had this experience. You put your code out there and people you have never expected to use it for purposes you've never thought that you never crossed your mind. Are using it and sending you emails and asking you questions about it. So it's really a very exciting new change in how people disseminate their work. It's very exciting.
Pull requests are very satisfying.
So one of the things that's fascinating to me about this evening is, I mean, who would have thought 10 years ago that a School of Engineering event would talk about using engineering tools like computers and software and algorithms and so on to study things like social networks and how they evolve over time, to study drug interactions and paleontology. I mean, the breadth of opportunities that comes from the ability to search databases and understand what meaning we can extract from them, it just really opens up incredible opportunities, I think, for engineers to work with other parts of this university. I think in a very real sense, many of the social science departments on this campus will be transformed over the next decade by hooking up with people from computer science to really use these techniques to understand things which they've never been able to understand through their traditional research methods. So it's an exciting time, I think, and I hope that you found the evening interesting and enjoyable. There are refreshments out back. I think our speakers will stay around for a while, be happy to continue the conversation, but we thank you all for coming, and let's thank our speakers one more time.